All right, so now we're going to say a little bit about the convergence of these iterative methods. For systems of linear equations. And so before we do this, I'm going to introduce what are called matrix norms. Okay. So this gives you basically a way to measure the size of a vector of matrix. Well, actually, the size of a matrix. But what we'll see is that it's induced by a norm on a vector. Okay. And so there are sort of many norms, and I'm just going to focus on one, so we'll only consider the infinity norm. Okay. All right. So anyway, so let's start with what we have. Okay, so let's say we're given a norm, given a vector norm on V, all right? So, and we have a linear operator that acts on V. All right, so so if you have a vector norm, we're going to construct what is called an induced norm or an operator norm on the space of linear operators on that vector space. Okay, so so again, it's like let's say we have V in this vector space V, and I have a matrix. Matrix A that acts on V. How do I measure the size of A given a way of measuring the size of vectors? Okay, so let's say we want to measure the size of this vector. One way to do this is to look at the supremum over all vectors which are less than equal to 1 in norm, and look at the norm of A times V, right? So A is, in this case, it's a matrix acting on the vector V. It gives you another vector. I can measure the size of this, and I want to sort of find the largest norm of this subject to the condition that V starts off having norm less than or equal to 1, okay? There are many equivalent ways of writing this. It's also sometimes written as the supremum over norm of V not equal to 0 of AV divided by V, right? So I should say that going from here to here, we need to assume that V is not just the 0 vector. Okay, so that V with just a 0 is still a vector space. Okay, so this being equivalent to this assumes that V is not the 0 vector. Okay, and again, if V is not just the 0 vector, you can also look at the supremum over norm of V equals to 1 of A V, right? So there's, so again, these two, well, okay. So these two are always equivalent. It's like, but this being equivalent to this requires that V is not just the zero vector space. Okay, but in general, that's sort of the most general setting. It's like which doesn't make any assumptions. Okay. All right. Anyhow, so the it's like the intuition, if you will, is that if I have some way of measuring the size of vectors, right, then I want to measure the matrix size in a way which says that, well, the matrix transforms this vector, and I want to know that the vector which comes out of it is not going to be maybe much larger than the original vector which came into it, right? So that's sort of the intuition. So if you have some sort of bounded operator norm, then what it's saying is that if you start off with some sort of finite vector, you can end up with some sort of finite vector as well. Okay, and that operator norm is going to give you a sense as to how much the size of the vector has been amplified by the operator A. Okay, so that's maybe a little bit abstract. So let's look at a simple example of this. As I mentioned, I'm primarily just going to focus on the infinity norm. Okay, so the infinity norm for a vector, as you might imagine, is just the maximum absolute value of the components of that vector. So I goes from 1 to m. So this is for the vector. Okay. And then you can check that given this infinity norm of the vector, that the induced matrix norm, which comes from that, okay, is just going to be the maximum of, again, I goes from 1 to m of the sum from j equals 1 to m of the absolute values of aij. Okay, so this is a matrix norm. So we might ask, it's like, why does it have this strange thing? Okay, and let me sort of use the one where the norm of this vector is 1, right? So so an example of this is when the vector is just this collection of ones, right? Well, let me write it as a column vector. Okay, so a times x, right, is then going to be a bunch of things which are the sum of aij. J goes from 1 to m, well, or a1j. Right. So anyway, and then you want to take the maximum over it, right? So anyway, so that's where this max over the sum comes from. Okay, all right. So in any case, so given the infinity norm on, so I should say that, yeah, then the, okay, so then the norm of ax, right, it's just the max over this sum. Okay, and then the absolute value part comes from the fact that instead of ones, I could have a -1, right? So I could have chosen 1 or -1. It's like, and it would still have had the same vector norm, right? And by appropriately choosing 1 or -1, it's like I could achieve, it's like this absolute value which I wanted. Okay. Anyhow, so hopefully that gives you the idea, right? That, depending on whether it's 1 or -1, it's like, you could either take the positive or negative of it. Okay. All right, so that's kind of a hand-wavy thing, but hopefully at least, it's like you get a sense as to why this might be a plausible operator norm. It's like associated with this infinity norm on the vector space. Okay, anyhow, that's just an example. The main point, or which is relevant in the convergence analysis of the iterative method for systems of linear equations, are the properties these matrix norms have with regard to the vector norms. So the properties as follows. Right, so the first one is that they have the triangle inequality, right? Right. So this is just a property of the vector norm, okay? And then if you have the norm of two matrices, the sum of the two matrices, that again has a triangle inequality. Okay, so at the level of vectors, at the level of matrices, okay? So if you take the product of two vectors, that's less than the norm of the product of the vectors is less than or equal to the product of the norms. Okay, and that follows again from from one of these many equivalent definitions. It's like of the operator norm. Okay, and then the fourth thing is that if you have a matrix acting on a vector that's less than equal to the norm of that vector is less than equal to the norm, operator norm of the matrix times the vector norm of the underlying vector. That's again sort of, you can see that easily for the definition of the operator norm as well. Okay, so anyway, so those are sort of some of the properties it's like you want. And then with that, it's like we're now in a position to talk about convergence of the iterative method, right? So, all right, so I'm going to define an error at the kth step as being x minus xk. So this error at the kth step. And so we know that nx k plus 1 is equal to b plus px k. All right, and that's the iterative, so the iteration formula. It's like, so the iterations satisfy this relationship, and then the exact solution satisfies the fixed point of that. So nx is equal to b plus px. Okay, so I can take the difference of these two equations, right? So 2 minus 1 gives me nx minus nxk plus 1. So that's n acting on the error at the kth plus first stage is equal to b cancels out. So I just have p acting on the error at the kth stage. Okay, so so this is again the defining equation for the fixed point iteration. This is the defining equation for the fixed point equation, right? X is a fixed point, is the solution of the linear system, exact solution of the linear system. This is just the iteration. The difference of this two gives me a relationship involving the errors at different stages. Okay. Okay, so if I let m be n inverse p, that means that the error at the kth plus first stage is equal to m times the error at the kth stage. Okay, and then once we have that, it's like we can evoke, you know, particularly this inequality to say something about convergence, right? Okay, so so that tells me that the error at the kth plus first stage is less than equal to, well, actually it's equal to the m times the error at the kth stage, right? invoking this is less than equal to the matrix norm of M times the vector norm of the error decay stage. Right? And I can recursively apply this relationship, and eventually I get that this is less than equal to the m power of the matrix norm of M, and then the error at the 0 stage. So, all right. So we know that. If the matrix norm of M is less than 1, then we have convergence. Linear convergence, right? And that the error is reduced by a factor of the norm of M each time. With each iteration. And we have a linear rate of convergence. Right, as the limit as k goes to infinity of the error at the cave plus first stage divided by the error at the cave stage is just this norm of M, right, which we are assuming is less than 1. Okay. And the convergence is independent of the initial guess. Okay. All right. So let's look at let's look back now at Jacobi iteration and Gauss-Seidel iteration and see under what conditions this matrix, the norm of M, is I guess less than 1. Okay. All right. So let's look at Jacobi. Right. So M is n inverse P, which is the following: 1 over A11, 1 over A MM times 0 A12 to A1M A210. So, all right. So anyway, hopefully you get the idea. All right. So that's the expression, and then the matrix norm in the infinity norm is the maximum over the sum all right. So if we want that the norm of this to be less than 1, this implies that the sum from j equals 1 to m for j not equal to I of aij is less than ajj for all I between 1 and m. Okay. So this is what is known as the diagonal dominance condition, which is to say that the diagonal entry in absolute value is greater than the sort of the non-diagonal entries in the corresponding row. Okay. Sorry, that's AII. Sorry. Okay, so this is what is called diagonally dominant. So the upshot of this is that Okay, if A is diagonally dominant, then Jacobi will converge. Okay, and then the same is true for Gauss-Seidel. And then I should make one further remark, which is that in general Gauss-Seidel will converge faster. Than Jacobi. And the reason is because the matrix norm of the Gauss-Seidel M is in general less than equal to the matrix norm of the Jacobi M, and we know that this is less than 1, again for diagonally dominant matrices. Well, I guess I should say that, well, you know, this inequality, this part of the inequality holds when you're a diagonally dominant matrix, and then this condition always holds, right? Okay, so anyway, so what we have then is that we now know that Gauss-Seidel and Jacobi iterations for this iterative solution of linear systems of equations converges at a linear rate, which depends on this matrix norm of n inverse p. Okay, and when you're looking at the operator norm, it's like on matrices, it's like which is induced by the infinity norm on vectors, right? Then this condition that the operator norm of that matrix n inverse p is less than 1 is satisfied. It's like when you have a matrix A which is diagonally dominant, okay? And so when you have a matrix A which is diagonally dominant, then Jacobi will converge with respect to the infinity norm in vectors, okay? And in general, it's like the Gauss-Seidel method is likely to converge faster because of this inequality, again, at the level of the operator norms. So with that, I will stop, and we'll pick it up later.